Understanding rational functions, proper vs improper. Okay, so let's begin our discussion on rational functions. As we move further into integration techniques, you'll frequently come across functions that are written as one polynomial divided by another polynomial. These types of functions are what we call rational functions. Now, before we can actually integrate these rational functions, that is, find their indefinite integral, there's a crucial step. We need to determine if the function is what we call proper or improper. This classification is really important. But just to give you a heads up, the integration technique we use, specifically, something called partial fraction decomposition, changes depending on whether the rational function is proper or improper. So, getting this distinction right is key to successfully integrating these functions. We'll be covering that in detail, so don't worry if it doesn't fully click just yet. Think of it like a fraction, but instead of just numbers, the numerator and denominator are both polynomials, expressions with variables raised to powers. What do I mean by proper and improper? Well, it all comes down to comparing the degrees of the polynomials in the numerator and the denominator. We'll be diving into that comparison in the following slides. What is a rational function? This slide introduces the general form. A rational function is simply a function that can be expressed as a fraction where both the numerator and the denominator are polynomials. We represent this mathematically as f of x equals p of x divided by q of x. Let's break that down. P of x and q of x both represent polynomials, expressions with terms containing variables raised to non-negative integer powers, like we've seen before. And crucially, q of x, the denominator, cannot be equal to 0. If the denominator is 0, the function is undefined at that point. Now, let's look at an example of a polynomial. Here we have p of x equals 3x squared plus 2x plus 5. Notice it's just a combination of terms with x raised to different powers and constant terms. Finally, let's put it all together with an example of a rational function. We have f of x equals 3x squared plus 2x plus 5, all divided by x cubed minus 1. See how the numerator, 3x squared plus 2x plus 5, and the denominator, x cubed minus 1, are both polynomials? That's what makes this a rational function. Okay, so now that we've established why it's important to distinguish between proper and improper rational functions, remembering that this impacts how we integrate them, let's first clearly define what a rational function is. Keep this definition in mind, because on the next slides, we'll be using it to determine whether a given rational function is proper or improper. We'll be looking specifically at the degrees of these polynomials, so pay close attention to that concept. Proper rational functions. Okay, so now we're moving on to the specifics of rational functions, and this slide introduces the concept of a proper rational function. Remember from the previous slides, a rational function is just a polynomial divided by another polynomial. This slide tells us that a rational function, written as p of x divided by q of x, is considered proper if the degree of the polynomial on top, that's p of x, is strictly less than the degree of the polynomial on the bottom. That's q of x. Let me repeat that. The degree of the numerator must be smaller than the degree of the denominator for it to be a proper rational function. Now, what do we mean by degree? The degree of a polynomial is simply the highest power of the variable, x, that appears in that polynomial. For example, in the polynomial 3x squared plus 2x plus 5, the degree is 2 because the highest power of x is 2. So, to summarize, the criteria for a proper rational function is that the degree of p of x is less than the degree of q of x. Let's look at an example to make this crystal clear. Consider the function f of x equals 2x plus 3, all divided by x squared plus 5x plus 6. Let's break it down. The numerator, 2x plus 3, only has x to the power of 1, that's just x. So the degree of p of x, the numerator, is 1. Now, let's look at the denominator, x squared plus 5x plus 6. The highest power of x here is 2. Therefore, the degree of q of x, the denominator, is 2. Finally, we compare. Is 1 less than 2? Yes, it is. Since the degree of the numerator, 1, is strictly less than the degree of the denominator, 2, this function, f of x equals 2x plus 3 divided by x squared plus 5x plus 6, is a proper rational function. Understanding whether a rational function is proper or improper is crucial because, as we'll see on the next slide, the method we use to integrate these functions, that is, to find the area under the curve, depends on whether it's proper or improper. So, make sure you've got a good grasp of this concept before we move on. Improper rational functions. Okay, so let's move on to understanding improper rational functions. As we discussed on the previous slides, recognizing whether a rational function is proper or improper is crucial before we can apply techniques like partial fraction decomposition. Now, a rational function, remember that's just a fraction where both the numerator and denominator are polynomials, is considered improper if the degree of the polynomial on top, that's the numerator, which we're calling p of x, is greater than or equal to the degree of the polynomial on the bottom, the denominator, q of x. Let me write that out as a simple rule for you. The degree of p of x is greater than or equal to the degree of q of x. What does degree mean again? It's simply the highest power of x in the polynomial. Let's look at an example to make this crystal clear. Consider the function f of x equals x cubed plus 2, all divided by x squared minus 1. Let's break it down. The numerator is x cubed plus 2. The highest power of x in this polynomial is 3. Therefore, the degree of p of x, our numerator, is 3. Now, let's look at the denominator, x squared minus 1. The highest power of x here is 2. So the degree of q of x, our denominator, is 2. Finally, we compare. Is 3 greater than or equal to 2? Yes, it is. Since the degree of the numerator is greater than or equal to the degree of the denominator, this function, f of x equals x cubed plus 2 divided by x squared minus 1, is an improper rational function. Remember, identifying this is the first step. If we encounter an improper rational function, we can't directly jump into partial fraction decomposition. We'll need to use polynomial long division, which we'll cover in the next few slides, to convert it into a proper rational function before we can proceed. Converting improper to proper functions. Okay, so let's move on to what happens when we do encounter an improper rational function. Remember from the previous slides, we established the difference between proper and improper rational functions based on the degree of the numerator and denominator. Now, this slide is crucial because it tells us what to do when things aren't quite right for our integration technique. First point, the method of partial fraction decomposition, which we'll be learning about shortly, can only be applied to proper rational functions. It simply won't work if you try to use it directly on an improper one. Think of it like trying to fit a square peg into a round hole. It just doesn't align. So, what do we do if we have an improper rational function? The second point tells us, if we encounter an improper rational function, we must first convert it into a proper one using polynomial long division. This is a key step, and it's all about getting the function into a form that will work with partial fractions. Now let's look at how that division actually looks. When we divide the numerator polynomial, which we're calling p of x, by the denominator polynomial, q of x, we can express the original function as the sum of two parts. This is shown here. P of x divided by q of x equals t of x plus p1 of x divided by q of x. Let's break down what each of those parts represents. T of x is the quotient. This will be a polynomial, and importantly, it's a polynomial that's relatively easy to integrate on its own. P1 of x is the remainder, what's left over after the division. And finally, P1 of x divided by q of x is a proper rational function. This is the crucial part. After the long division, we've created a proper rational function, and that's what we can then decompose into partial fractions. So, long division isn't just some random math skill we're pulling out. It's a necessary step to prepare the improper rational function for the integration technique we're going to learn. We'll see this in action on the next slide with a concrete example, so you'll get a really clear picture of how this all works. Step-by-step example of conversion. Okay, so let's tackle an example of converting an improper rational function into a proper one, as we discussed on the previous slides. This is a crucial step before we can apply partial fraction decomposition. Here on the slide, we have our problem. We need to convert the function f of x, which is equal to x squared plus 3x plus 5, all divided by x plus 1, into a proper form. Step 1 is to identify the degrees of the numerator and the denominator. Remember, the degree of a polynomial is the highest power of x. Looking at our numerator, x squared plus 3x plus 5, the highest power of x is 2. So, the degree of the numerator is 2. Now, let's look at the denominator, x plus 1. The highest power of x here is 1, so the degree of the denominator is 1. Since 2 is greater than or equal to 1, that confirms that this is indeed an impediment rational function, just as we defined earlier. Now, step 2 is where we perform long division. This is just like the long division you learned in arithmetic, but with polynomials. We're dividing x squared plus 3x plus 5 by x plus 1. Let's go through it step by step. First, we look at the leading terms. The terms with the highest powers of x, we divide the first term of the numerator, which is x squared, by the first term of the denominator, which is x squared divided by x equals x. This x becomes the first term of what we call the quotient, t of x. Next, we multiply this x by the entire denominator, x plus 1. X times x plus 1 gives us x squared plus x. Now we subtract this result, x squared plus x, from the original numerator, x squared plus 3x plus 5. When we do that subtraction, we get 2x plus 5. This is our first remainder. We repeat the process. We now look at the leading term of this new remainder, which is 2x, and divide it by the leading term of the denominator, which is still x. 2x divided by x equals 2. This 2 becomes the next term of our quotient, t of x. We multiply this 2 by the denominator, x plus 1, which gives us 2x plus 2. Finally, we subtract this result, 2x plus 2, from our current remainder, 2x plus 5. This leaves us with a final remainder of 3. So, we've completed the long division. Remember, this remainder, 3, is key to getting our function into proper form. We'll use this result on the next slide to rewrite the original improper function. Write the final expression. Now, after performing polynomial long division, and I encourage you to review those steps if they're not completely clear, we've arrived at our quotient and remainder. Here's what we found. The quotient, which we denoted as t of x, is simply x plus 2. The remainder, which we called p1 of x, is just the constant value 3. And of course, our original denominator, q of x, remains x plus 1. This allows us to rewrite our original improper rational function in a much more useful form. We can express the original function, x squared plus 3x plus 5, divided by x plus 1, as the sum of the quotient and the remainder divided by the original denominator. So, that's x plus 2 plus 3 divided by x plus 1. Notice something important here. The term x plus 2 is just a polynomial, and we can integrate that easily using the basic power rule for integration. More importantly, the remaining fraction, 3 divided by x plus 1, is now a proper rational function. Remember, a proper rational function has a numerator whose degree is strictly less than the degree of the denominator. And why is that important? Because, as we discussed at the very beginning, partial fraction decomposition, the technique we'll be using to integrate this only works on proper rational functions. So, we've successfully transformed our original problem into a form where we can apply that technique. We've broken down the complex improper fraction into a manageable polynomial part and a proper fractional part, setting us up for the next step in the integration process. Okay, let's wrap up the conversion of our improper rational function. As you recall from the previous slides, we were working with the function f of x equals x squared plus 3x plus 5, all divided by x plus 1, and we determined it was improper because the degree of the numerator was greater than the degree of the denominator. Common mistakes to avoid. A very frequent error I see is students jumping straight into partial fraction decomposition without first determining if the rational function is proper or improper. Remember, partial fraction decomposition only works on proper rational functions. That is, functions where the degree of the numerator is strictly less than the degree of the denominator. If you try to apply it to an improper function, you'll end up with a system of equations that just won't solve correctly. You'll get nonsensical values for the constants you're trying to find. So, the very first thing you should always do is compare the degrees of the numerator and denominator. This one seems simple, but it trips up a lot of students. The degree of a term is the exponent of the variable, not the coefficient. For example, if I write 5x cubed, and I'm saying that as 5x to the power of 3, the degree is 3, because 3 is the exponent of x, the 5 is the coefficient. It just scales the term, but it doesn't affect the degree. Keep those straight. Now, we saw on the previous slides that if you have an improper rational function, you need to perform polynomial long division to convert it into a proper one. During that long division process, especially the subtraction steps, it's incredibly easy to make a sign error. A single mistake with a plus or minus sign will throw off your entire remainder. And remember, that remainder, which we called P1 of x, is crucial for setting up the partial fraction decomposition. So, double-check your subtraction carefully. Take your time and ensure you're subtracting correctly. Okay, let's move on to slide 8. This slide highlights some common mistakes students make when dealing with rational functions, and it's really important we address these before you start tackling more complex problems. By being aware of these common pitfalls, you'll significantly reduce the chances of making these mistakes and ensure you're on the right track to successfully integrating rational functions. Now, let's move on to the final slide where we'll recap the key takeaways. Key takeaways. First, remember that a rational function is simply a polynomial divided by another polynomial. We represent this mathematically as p of x, divided by q of x, where both p and q are polynomials in terms of x. Next, let's talk about proper rational functions. A rational function is considered proper if the degree of the polynomial in the numerator, that's p of x, is strictly less than the degree of the polynomial in the denominator. That's q of x, remember. The degree is the highest power of x in the polynomial. And importantly, proper rational functions are the ones we can directly apply partial fraction decomposition to, as we'll see in future lessons. Now, what about improper rational functions? Well, a rational function is improper if the degree of the numerator, p of x, is greater than or equal to the degree of the denominator, q of x. If you encounter an improper rational function, you cannot jump straight into partial fraction decomposition. That brings us to the goal of division. If you have an improper rational function, the first thing you need to do is perform polynomial long division. The purpose of this division is to split the original improper function into two parts: a polynomial, which we call t of x, and a proper rational function, which we call p1 of x, divided by q of x. The polynomial t of x is easy to integrate, and the remaining proper fraction can then be broken down using partial fractions. Okay, let's recap everything we've covered regarding rational functions, proper and improper fractions. This slide serves as a nice summary, so pay close attention. So, to reiterate, we identify if a function is proper or improper by comparing the degrees of the numerator and denominator. If it's improper, we use long division to create a proper fraction that can be used with partial fraction decomposition. This is a crucial step, so make sure you understand it well.